Good evening, gentle readers. Today is July the 15th, 2024, from a desk with Ross Finlayson here in Seattle, Washington. I hope to relay some more of these talks since the beginning of Moment and Motion, the geometry of motion. Geometry is motion. And these kinds of various approaches to a unified approach to these questions of how the change is defined as a constant or quantity, and these the vagaries, the vagueness, which results the well-formed, the defined of things that move, and how and why they do, and particularly how much they do, with regards to the mathematical physics for the quantitative after the qualitative. There was several times mentioned the distinctions of quantification. One is just sort of the comprehension of a variable, the apple, as a thing in the universe. And the other is of something like a particular finite quantity, itself. And so it helps to just reflect upon these complementary duals and the very relevant nature of nature itself, but of universals and the importance of looking at things as if they have two sides. Vis-a-vis induction and the inductive inference, which we can define as a course for carriage, as is something that's so and so for the next, and true for a rule. And exceptions as rules, and rules are exceptions, and exceptions are rules, which make it so that we can find for a given system, when it has at least two rules, that it results as to one. The meeting after the bridging of the inductive impasse, the meeting in the middle of nowhere, as is a regular enough touchstone of these talks. Well, today, as usual, it's not a very structured sort of approach, not much of a plan, but I do have here copies of the Feynman lectures in physics, and so these were supposedly kind of impromptu themselves. It is well reflected that whereas I'm more of a journeyman sort of computer programmer and software engineer, his life was bread and butter, the physics, and quite all involved with everything. So it comes across as pretty well informed, a lot of the different things. And then as with regards to, he had particular specialization, if I'm somewhat a generalist in these matters, of the electron physics and this kinds of approaches that make it so that for the kind of the sum of history side, then as we look more for the sum of potentials side of things, as for what was and is and what is to what will be, the sum of potentials, thus that for our theory that it's satisfied as criteria of including the principle of least action, along with all the most other usual laws that deductive inference arrives at must be the laws of physics, make for a theory overall. So I imagine then I'll just take a look through these a little bit and kind of see what I have to find of them. He's been gathering dust for a while here. So this first one is volume 1, and there's volume 2 and volume 3 of these voluminous notes of coverage of quite a few interesting subjects in the mathematics and physics, but mostly about the physics and just the least amount of mathematics necessary to arrive at the most amount of physics. Because as we looked at things that that get to involving the higher mathematics, and it becomes more and more difficult to keep that related in terms of simple systems of application. So for something like the wave equation, for example, or something like the even just this force equals mass times acceleration and the infinitely many higher orders of acceleration, that it gets to the notions that, well, the wave equation can go any of a number of different ways, which is infinity many. So the way it works out is people say, well, let's just say it's kind of random and add those up. And there's the whole sum of histories bit, that the sum of potentials is all the different things. That to take an approach to it, it ends up kind of requiring a higher mathematics involving these continuous domains and laws of large numbers that are beyond the laws of small numbers, as it were, are classical, and most classical law, and that afforded by inference all the way out, that this number is small, and the next number is also small, and the next number is also small, ... all the way out to infinity, then that for large numbers that they're large in various ways. These the biggest and then bigger infinity, kind of inverting the superlative and comparative as it goes, making for these complements of the three continuous domains and three laws of large numbers, three kinds of Cantor space, and maybe more, but three at least is enough to get started. When first for many people there's none, and then for everybody else there's one. So these are the kinds of things that help make for an original analysis for when zero is just nothing, to when it's the center, to when it's the end again. Of these kinds of concepts in mathematics that arise purely for themselves, just like an axiomless geometry arises from axiomless natural deduction, a point in all the space, just from the terms, that this makes for quite a thorough reckoning of all these things for the theory, which makes for foundations that it's possible to consider having one at all in this postmodern approach. After Gödel said everything was incomplete or inconsistent, you can say, well, we have something at least that's complete and consistent again. Or after the quantum mechanic approach is like, it's all random, it will never arrive at anything that people can actually comprehend. It's like, well, no, it's just superclassical, paleoclassical, and then superclassical, using the fact that, of course, from the ancients, there are these same kinds of concepts of, the spiral space-filling curve, or things to do with Aristotle's, at least there's two continuums, and particularly Zeno of Elea's thought experiments and arguments helping explain that there must be, after infinite divisibility, continuous uniform motion, reflects the clock hypothesis, which has a little bit wider setting in terms of there being a universal time than some have it. And then also with regards to the fourth dimension and the discontinuity after the application and naive properties of mechanics in space-time help to reflect that that can be made again with the same rules and the same mathematical transforms and laws back into something that is a little bit more together and a little bit less kind of the end of continuity or the end of causality or the end of consistency or the end of completeness, kind of reflecting on there was an earlier discussion on the teleological principles, and so it was reflected upon that there was Wittgenstein, Nietzsche, and Heidegger, and so one's kind of like the end of consistency, the end of deity, and then the end of time. And so getting back above that stuff again and kind of drawing through the silver thread again and showing that we can have just this mere skein of teleological principles, and it's a metaphysics, all right, but there must be one. The theory to have a meta theory, to have a working theory, is just still has to be that same theory again. So that it's possible then this way to look at the richness built from these fundamentally new concepts: curved space-time, quantum dynamics, or otherwise these things that help bring up what are these principal concepts of the particle wave duality and these kinds of things, the complementary duals, to help associate and them with the canon of philosophy and its concepts, thusly Kant's sublime, the indicators of higher reasoning and these kinds of things, to point that all the way back at Plato's noumenon, or the concept of the oneness of things, and that it exists for us to discover this true logical mathematics. It's great. It is the way it is, and it allows one to both be like totally comfortable with all of canon, to have the profound apologetics for modern logical positivism and real result the stronger one, and then also to not have to figure out how to explain things by like multiple worlds or divergence in space-time, when There's no such thing as such a negative quantity like that of negative time or these things. It is real again. So that's something that can be appreciated, and it doesn't necessarily impinge on free will, which is just its own thing, and it doesn't necessarily say anything at all about like unfalsifiable pseudoscientific concepts like a digital universe or whatever, because it doesn't matter. It just doesn't matter. And the reason can still arrive at like, well, the real theory is in there, you know. That goes very well sometimes. So there's 50 chapters here, 52 chapters. 52, always good goal. So rotation in 2 dimensions, center, mass, moment of inertia, rotation, space, a harmonic oscillator. See, the oscillator starts to reflect something because it's kind of like, well, there's no perpetual motion machine, but an object that's spinning is never going to stop. But the idea of the perpetual motion machine is only that you cannot extract work out of this thing without expecting it to change somehow. To extract work on it eventually implies applying a lever, this being the most simple machine that's been arrived at for the whole kinetics and kinematics, that is always just a fulcrum as something about shifting about a lever or being affected, is that the simplest machine there is also kind of this micro machine and used to affect it. There's white holes everywhere, and there are also white holes and black holes everywhere of a tiny, tiny scale. We call them matter. In terms of like, well, on one hand they draw in, on the other hand they let out. And this tiny lever is everywhere, helping to affect reflect. And this is one thing I wanted to mention today, that it's orbits. Everything is in orbit about everything else. It's not so much that the universal theory of gravity is that we're all drawn together by the perpetual work being done by massive bodies for each other, but instead it's like there's just something in the universe that like everything just kind of floats, and then when there's something to block it from either side of the universe, they float together because that it helps explain the same quantity, inverse square, and also the fact that in the large scale it's not quite exactly that, but it becomes more like a shadow of the things that it falls into instead of like the gravity beam pulling them together or something like that. That's one thing I haven't thought about for a while, a tractor beam or something like that. The Star Trek physics was largely understood to be like, well, that's impossible. It's a fantastical science fiction. And some of it is, most surely, you know, but they could all just be living in a simulation of sorts. But some of it is a little bit less far-fetched when it's possible to consider how there could be, for example, warp drive. Because, for example, last month, some guys came up and said, hey, you know, we found a way to do sum-of-histories before sum-of-potentials, before we only had sum-of-histories, to arrive at in special relativity that C isn't like a speed limit for the universe. And maybe that'll help explain, like, when we look to the sky and we see relativistic jets that are, like, flying much, much faster than the speed of light, officially. That way it's no longer just an illusion. I mean, science doesn't involve the theory saying it just, we can't believe our eyes, because, you know, that's just one of those things. With regards to something like some years ago, it was said, oh, a laboratory invented quantum teleportation. Still, time travel is right out, except for forward in time, unless you're living in a simulation, which is a different thing. Or thrown in a black hole to diverge histories forever. So anyways, the tractor beam or disintegrator ray or lasers or lightsabers or any of these kinds of things, they do have kind of how you can theoretically on pencil and paper figure them out. It is the way and all this kind of stuff. So it starts with quantities, time and distance. You know, here that's one thing we've been talking about, time and distance. Because the idea is that distance and travel and length are the same units, length. At the same time, there's all these implicit units of time associated with it. So like, length is length is length is length. It's a meter. It's a metric. It's got a metric. It's at rest. And distance is like the length and the time, with regards to everything else about it. These units all cancel out and result that they're just the same unit together at the end. But the quantifier, the quantification of that, has all the implicits all in front of it, infinitely many, relating to everything else in the universe. And so trying to figure out that, well, in the large scale, it just so is that the grain of things is so that makes for y that it results that inverse square is the perceived force that draws bodies together as the perceived force of gravity, when this mechanism could just be the opposite. Is like objects just in their orbits occlude and block and provide a shade, basically a shade of gravity's rays that are these weakest force from the utter edge of the universe. Kind of like in terms of the usual model of light and shadow. So that's why it's also something called a shadow gravity, to help describe that these features aren't exactly Newtonian, which are Galilean and Keplerian put together with a bit of calculus. What is energy? Gravitational potential energy. So here gravitational potential energy goes to help have that. Well, it's like this energy's got to be conserved. So what goes up must come down. And so to have that there's this energy from gravity, it's like something at a sufficient height that it can then drop. It raises, as it raises to a height, it gains potential energy as it loses energy in its rise, and then it falls back down, exactly balancing that out. So this is just another reason to show that, hey, the way to look at these real quantities, they must all be potential quantities of a sort. So like always, instead of like two kinds, that this bookkeeping is like, well, it's like the apple in the entire universe about it. Potential, actual. That also the potential fields are real. And finally, the classical linear moment in the middle also is a real potential action. That then is also immediate. And usually so. Of course, where on the way to that any actor, given the information, can so simply compute right or left, up or down, as by the application of a lever at any particular instant. So guaranteeing minimization or maximization of otherwise what would be consequence events. And thus what are consequent events? What will be, will be. The future is not yet written. I'm lucky, I don't know if it's luck or bad luck, but by now I've collected an entire grab bag of little phrases, so that as I'm going along in this rambling extemporaneous course, I can always just kind of arrive at a few old gems, to help affect, to reflect, which is another one. That these things like the sum-of-histories, sum-of-potentials, becomes well defined and has a constant sort of meaning throughout. And then it's also a reference to these other things. So looking here at these units and standards of time, Feynman's written a chart, and it's got the time scales of the universe. So he's got 10 to the 18. Now, one thing we know from the Sky Survey is that every 5 years, at least, the universe gets about 1 billion years older or more, because as more sensitive experiments come online, then entire backfields of information were just light up. And so that has really made it so that the James Webb Space Telescope out of the Lagrange point, or what, one of the most profound technical accomplishments of civilization, has really paint-canned inflationary cosmology and really made it so it's like, those are definitely superluminal jets these galaxies definitely are holding themselves together, or they're just not spinning apart. They're just rotating a piece, free rotating frames. And the age of the universe has gotten much, 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 much older since this went online. So now every 5 years, it's like the universe just got a lot older. This chart starts at like 10 to 18 seconds ago, and there's more of them. Then the Big Bang Theory then starts as like, well, let's think of it, and this was in a different time. It was the 1920s till about 2010, and before, and since, but it's a profoundly tuned kind of science with the Big Bang Theory out to the inflationary epoch and all this kind of stuff. That's like, well, we're going to start with just like what would be the soup that results after like 10 to the negative 45 seconds, that all that came in and then resulted stuff that then separated into matter and all the matter and antimatter combined. It made like the chirality or left or right-handedness of the universe, and so on, so forth. Still has that. Neither the Big Bang nor the steady state hypothesis for the universe is falsifiable, because ultimately you can go all the way back to infinitely far in time looking for it, and it would not arrive. Yet either it can be made a model and tuned to it and made to fit so that everything in the local, which can be pretty much the global, would apply to it. So then he gets up to the middle is life of a man, 10 to the 9 seconds. And then he's got something like the 1 heartbeat is 1 second he has here. Light travels a foot in 10 to the negative 9. Radio waves are about 10 to the negative 8. Wavelength, period. Molecular, atomic, light crosses an atom. Nuclear vibration, light crosses a nucleus. Down to 10 to the 24. So then this 10 to the negative 24 is basically the atomic scale. And so that's in mass and here time scales. So they're about the same. And it's funny that in the very, very small, the quantities, as they rotate, essentially, in this free rotation bit, become kind of conflated. It's kind of indistinguishable, the mass and time and length, and charge, I guess you might say. And so why that's relevant in a thing is because for the running constants in this kind of thing, and to help understand that in some of these superclassical models, that it's only to make it so for that's just a functional freedom. So out of those still emerge back then, these perfectly linear things that are made of them. But as the effects become the atomic and subatomic, or the Planckian and transplanckian, that there is the geometric mutation of the units is about each other. So this is a pretty high-level concept in physics. It's related to the running constants, which we've encountered just now at the age of the universe, always getting older. The size of the particles always getting smaller with the configuration and energy of experiment. 10 to the negative 25 is about as smaller than us as atoms are smaller than us. 10 with 25 zeros. And then superstrings theory is just like twice that is continuous if it's grainy at all. Quantization is a little bit different than quantification, but it's also kind of the same. Quantization is saying this is ultimately fundamentally of too fine a particulate grain to assign it any analytical character at all. So we have to do so because that's the only way we can measure things and give them units for dimensional analysis. And then this is called normalization and renormalization. It's after denormalization to arrive at these quantities, that the whole electron physics bit and spectral physics are like, we found a very, very narrow course and it happens to add up in the middle. We're going to call that 1.0. build everything else upon that. And then all this other stuff that has to do with stochastic interpretation and everything in quantum mechanics has to do with that. Quantization. So this, making it back to a continuum mechanics, is its own kind of thing. So that's this chart here. And he talks about the half-life of radioactivity of the chemical elements, of the elements of matter, in the states of matter, the elements of matter, helping to reflect it, just like we were just thinking about charge, mass, time, and length. And then there's charge, mass, and the lifetime of matter and the speed of light, or how far it goes. That make it so that these are two kinds of these same things that happen from the very fundamental distinctions and contradistinctions of the matter and this and that, and the units and the dimensional analysis, which make it so that these are reasons why it's arrived at that physics is a bit richer and fuller, because mathematics is a bit richer and fuller, that these quantities are energy and waves, the fungible objects of the milieu of physics, yet still kind of having this combined milieu, where at the same time they're apart for each other. So in this way, energy and the quantization and the fundamental forces, and why there are four fundamental forces, yet it's unified field theory, and why there are effects of the quantization and the infinitesimal, and then of the quantization in the grainy and then the smooth again, and of the continuum mechanics, that it's the continuum mechanics, help explain all kinds of things why it's one unified theory, while not necessarily needing it all to have anything like another one. So let's see what Feynman's got here. He's got a chart. He's got Earth around the sun and the North Star. And it says Earth winter location, summer location. The distance to nearby stars can be measured by triangulation, using the diameter of the Earth's orbit as a baseline. The height of a Sputnik is determined by triangulation. So it's talking about triangulation, then it's about parallax. So parallax is the most usual way that stereographic range finding occurs. And it's a common feature of all sorts of stereoscopic vision. And then it's also used for all such manners of reckoning. And then the idea of parallax has another notion, this peripheral parallax. So peripheral parallax is this idea that there's a consequent quality associated with vision, and it's not just because eyeballs are orbs, yet it's so related, as to why when we look to the heavens, why it's like a big copper dish. The peripheral parallax is part of the concept that helps explain why the optical light is special. It gets around. And so the idea that the peripheral parallax is another kind of complement is also reflected in these principles of motion, because what it gets involved with is that the parallax is fundamentally linear and direct and straight. And so this peripheral parallax is orthogonal and perpendicular to the things, as well reflects that it says of the consequence of the optical nature of light, besides the purely geometric and straight ray-like quantity of light, the light is optical and flexes it all, or focuses. So peripheral parallax is a complementary concept to parallax in triangulation, as what is on page 5-6 here of Feynman's notes. He talks about standard candles and meters and measures. 1,000 equal subdivisions of the millimeter to make a scale of microns, millionths of a meter, or micrometers. It is difficult to continue to smaller scales because we cannot see objects smaller than the wavelength of visible light. And visible light is kind of special optically. So optical light and nuclear radiation are different things than electromagnetic radiation that happen to live in the same kind of milieu. So the idea that the electron and photon are these same particles in one electromagnetic spectrum is a conceit, and it's erasing the difference of what is otherwise two different things that just happen to be otherwise kind of indistinguishable by the character. So then as we get to the atomic scale, and then above that angstroms, which is like, this is where the optical ends, and below that Planck length, which is like below this is below where the angular momentum makes sense to the linear moments of the atom anymore. All one theory, all one thing. Helps show that light is special, light is optical, and that the electromagnetic is magnetic in terms of its relation then in these fields of a unified field theory that's all four fields in one space-time field. They have one of these now. I brought one with me. Here's the table now of distances. So it's got distances. Edge of the universe, 10 to the 27 meters. Radius of a nucleus, 10 to the negative 15 meters. Again, with people, the mesoscale is in the middle. So we call that the macro scale and the micro scale. There is a large gap, as it reads Feynman, there is a large gap in physical sizes between the typical atomic dimension of about 10 to the negative 10 meter and the nuclear dimension is 10 to the negative 15 meter, 10 to the negative 5 times smaller. For nuclear sizes, a different way of measuring a size becomes convenient. We measure the apparent area, sigma, called the effective cross-section. If we wish the radius, we can obtain it from sigma equals pi r squared, since nuclei are nearly spherical. Measurements of a nuclear cross-section gets into that measuring tons and tons of small things is measuring their flow over time. And really, that's the only way it's done. And even saying that electrons and photons are particles is kind of contrived. Because it is particle wave duality and it is waves. And the particle aspect is the interactions of them. That results taking place here in this particle physics, in this angstroms to Planck scales. Where the wave particle duality goes on down below the Planckian regime, and the wave resonance duality is up above. It can be made by nuclear cross-section can be made by passing a beam of high-energy particles through a thin slab of material and observing the number of particles which do not get through. These high-energy particles will plow right through the thin cloud of electrons and will be stopped or deflected only if they hit the concentrated weight of a nucleus. Another way to look at that is that particles never deflect, but they only ever orbit each other so briefly and fly away. Do this slingshot effect. Vis-a-vis the very, very, very utterly opposite one, where it's like one actually collides, like usually it's a kinetic model, it's after billiards, and it's like it collides, it's like a croquet ball, it flies away. Here it's that it's like, well, it flies and it flies so close to the central moment that it orbits, that its trajectory changes just only according to that. The deflection is not really the right thing. So when we're trying to figure out these cones and the angles and these other aspects of the diffraction and reflection, this kind of stuff, it's one of these double reverse things that arrives at the same thing. Now one might say is like, well, three left turns doesn't make a right turn. Oh wait, yeah, it does. But two rights are just one right. Two wrongs do not make a right. So that's different, though. It's always a great day. Some better than others. So anyways, suppose we have a piece of material 1 centimeter thick. There will be about 10 to the 8th atomic layers according to this model, apparatus and its description, and the convention, and what's built up is the empirical and how it reads out, and the fact that Feynman's an expert in electron physics, and he will write anything about it in terms of them, which he does just great, and it's fantastic. But the nuclei are so small that there's little chance that any nucleus will lie behind another. So he talks about the chance that the cross-section will be arrived at. From such an experiment, we will find that the radii of the nuclei are from about 1 to 6 times 10 to the negative 15 meter. The length unit 10 to the negative 15th meter is called the Fermi in honor of Enrico Fermi, a great inventor in radio technology and such. What do we find if we go to smaller distances? Can we measure smaller distances? Such questions are not yet answerable. So this is from the 60s, but he says it has been suggested that the still unsolved mystery of nuclear forces may be unraveled only by some modification of our idea of space or measurement at such small distances. Indeed, and I haven't read this particular quote before. I've never really gone through these, page for page, but the theory that there's kind of like the Big Bang is a soup is like, well, so is subatomic soup. And then out of it rises all these, it's alphabet soup, all these letters. That's the way it is. And so Feynman hints to that we would need a physical model equipped with a mathematical model equipped with these concepts to arrive for these dimensional analyses and their units, why it's so, that it's so, and like so. Then he mentions natural units again. It's like, well, once we get down there, just call it 1.0. And then everything from up above, that'll be 1.0, and everything from below, that'll be 1.0. And that's why we got one atomic mass unit after one electron physics, and that's why we get Avogadro's number and all the rest of the great stuff of classical, modern atomic theory. So, and then he says something about the terrestrial, and it's like, hey, the Earth's our only experimental laboratory setting, so you might as well have the natural unit be like half Earth radius or something like that. It is currently being considered the new definition be adopted, an agreed upon arbitrary number of wavelengths of a chosen spectral line. And that is... the SI units are very focused on the special relativity satisfaction, and that makes it easy to use them directly as primitives, and just like now you can throw the units away and just deal with them as bits on the machine for computations and stuff like that. There remain many different empirical settings of units that have translations according to various configurations and energy of experiment, of course, to System International, our standard units, which are not always so relevant. They lose their attachment to the real part, but which are for all such classical matters, of course, perfectly suitable for anything. A meter is a meter is a meter. There is a norm. It's the same around the world, at least. Though gravity does vary by 1 or 2 decimal points around the world. So the next chapter is probability. He says chance. So there's certainty and uncertainty. There's probability and conditional probability. All such matters of quantum mechanics are built in terms of conditional probability. the Brockett notation or Dirac's notation is very much centrally associated with the Gaussian analysis after the Eulerian Gaussian analysis to make it so that these quantum amplitudes can be built up as after a setting of the stochastic interpretation to make it that then there's the ways to add up all the quantum amplitudes and arrive at something that's along the lines of an addition formula for same. But time, chance, and uncertainty has a lot going on. There's kind of like hearkening to the three laws of large numbers, 3 Cantor spaces, 3 continuous domains, and 3 types of probability have this 3 types of uncertainty. The Bayesian uncertainty, which is conditional probabilities by the usual classical laws of the finite. And then there's Jeffrey's uncertainty, which is a little bit different. And I'm not quite sure exactly how, but it's kind of like the log normal to the Gaussian. It's not too completely different, but at least it's askance. And then this Knightian uncertainty, which helps the effect to reflect that, you'd be surprised because after something kind of drops off and goes and has its critical change, and it has this really, really long tail, and it's kind of goes on forever. So that otherwise this whole world was built and it was like, what's the rule? It's we got a law of large numbers. It's a law of small numbers. Our Cantor space, well, we got to deal with that. Well, it's just forget about it because it's got no real analytical character we can deal with. And then there's something about the laws of continuous domains. It's like, well, yeah, we always have 0, 1, but then we just have regular field numbers, and there's no infinitesimals, so everything's finite or 0. There's no infinity either. It's simple this way. And then the probability is like it's Bayesian, which is kind of like for the central limit theorem of probability. There's like, well, the probability anything with any distribution with a mean, if you add up enough of them together, then it will have a mean and will look like the bell-shaped curve Gaussian distribution. It's like, okay, what about ones that don't have a mean? It's like, well, that's the idea. Some things are polarized. They don't have a mean. What do we do for all them? It's like, nobody knows anything about that. The entire theory does not really address that at all. So when you have say, some kind of dispersive limit theorem, and then this uniformization limit theorem is like, well, what's in the middle of that? It's like, it's uniform, it's flat, it's fair, everything's the same. So in this kind of theory of foundations, it's one theory, it comes from nothing, but there's at least 2 sides of things, and there's at least 3 definitions of infinity, continuity, probability, and statistics, or uncertainty, and the space of all the zeros and ones. There's 4 forces, which in the classical are all completely different, and in the micro are all the same. Gravity is there's this one force overall. It's kind of like, and it's also kind of the other ones, This is pretty much the smallest mental lunchbox necessary to have a nutritious word soup of the entire mortarboard of this concept of after axiomless natural deduction, a stronger mathematical Platonism, a stronger logical positivism, and a theory of everything, of course. There can only be one theory of everything. There can only be one. There is one. This is arrived at. So Feynman reads, he says, sometimes we make guesses because we wish with our limited knowledge to say as much as we can about some situation. Really, any generalization is in the nature of a guess. That's fair, and that overgeneralization is usually unsound. But there are universals which demand that they cannot be anything yet universals. That's by their very nature, universe. It's inclusive. These are the kinds of things that have boggled the minds of thinking beings, fellow earthlings, forever. Then he talks about Bernoulli trials or flipping a coin. A fair coin toss results 0 or 1 or -1 or 1. Figuring that on the average it would add up to 0. This makes for that there's 3 kinds of Cantor spaces. So when you think about all the infinite sequences on zeros and ones, how it could add up that half of them go one way and half another, or half stay in one place and half move, or most of them are average and a few are extreme, or vice versa. These are just usual kinds of things. Usually having these macroscopic tendencies driving everything. The whole sum of potentials this way is like it's what it goes into. It's what it grows into. These kinds of things. Mentions probabilities, sampling, fluctuations. Here that's framed in terms of attenuation, dissipation, and oscillation and restitution. But then it also gets related to the flux when we have the flow and then the flux, with the flux being the concept of like the superclassical flow, like when something's melting and it flows, and the flux is like when it breaks down its capillarity and then fills the joint or something like that when you're welding something. Or that the flux is like, well, when a mass of grain piles down the chute, it's the air that rushes backwards. Or that light is flux is the most usual idea, that the fleeting form of light is as a flux. And so fluctuations are fluctuations of the sort that would vary so very rapidly that they are effectively distinguishable by the fact that they vary rapidly. So this is kind of the definition of the term, which as of usual good definitions have to be the same all the time. And when they're not, demand their deconstructive account on how and why and all the other question words, they are not. To put them back together again is reasonably well-founded. The random walk is another good concept. How do we get there from here or there? Why or why not? Answering the question words for all the terms, predicates, their relations. That's deduction usually is the answering the things vis-a-vis the providing the answers, the determining what are not the answers, and carrying on. Probability density. So he helps describe that there's a mathematical function for a probability distribution that's always like the sample space. For this, there's in some of these earlier talks, there's been covered these kinds of concepts, like a brief introduction to probability theory. It's a function with area 1. Throw a dart at it. That's your pick. You know, that's how they add them up. That's it. Add those up. Divide them by how many. That's one probability distribution. Mathematically, it's a function under which is an area equal to 1. That's never less than 0. Also is the other thing. So that's the thing. The uncertainty principle. Now, the uncertainty principle is a pretty funny thing because it gets into the sampling, observer, and measurement effects. So what are these is that it's like, well, anytime you take a sample, observation, or measurement, you're essentially interfering with the system. That it is so, kind of like in the discussion of the intromissive and extromissive and the active and passive modes of sensing, that pretty much when you stick a fork in a light socket to see if current is flowing, you're interfering with the system. And so it could, cause a short circuit or anything else that has to do with the fact that when in these quantum states that are so particularly contrived as defined by their sum potentials, anything that causes a polarizing moment to them is interference of a sort. So how does that relate to the Heisenberg uncertainty principle? This says we've got as perfectly accurate an emitter as we can determine by the time that we can trip it, and a perfectly accurate detector as we can determine as we can detect when the ray of light or the stream of electrons arrives. So given that, and we know the formula between A and B in the time T0 and T1 when it arrives, and given that it's perfectly well understood what is the value then can we determine the position and momentum of the object at the detector? So according to this argument, it's like, well, yeah, that's Heisenberg's certainty. It's Galilean. It's like this. But the Heisenberg's uncertainty is like, well, when a position and momentum is off, because they're a function of each other in terms of the wavelength for these particles, that as one tips over the other side and one tips over the other side, that it grows depending on how much that uncertainty is, so as to that it arrives as like a probabilistic wave or as of a superclassical action associated with the wave. So in that sense, it's formally why there's both Heisenberg's certainty, which is not the usual thing at all. Nobody will ever tell you in a class other than this, Heisenberg's certainty. Heisenberg uncertainty is a simple matter of saying it's because we've had to normalize this concept of this entire sum of history, sum of potentials as a particle, that's why we say that then that particle has got this or that or the other. Uncertain, one or the other. If you know the position, you can't really know the momentum. If you know the momentum, you can't really know the position. Yet when it arrived, it has exactly the same. So it's formal that way, why it is so, and it's a very profound concept, because otherwise when people are just learning the concept of the linear particle and all they have is a particle model, they can't get particle wave duality without that. So it's critical to have the Heisenberg uncertainty, because otherwise you could say, like, I don't need particle wave duality. It's straight line A to B. It's a billiard ball mechanics. Well, see. Then after that, it's like, well, now you need to repair that concept twice, because it's a great concept, but what it provided was a conceit, a concession to these other aspects of it, which are true, which were neglected or discarded. So then to pick those back up involves kind of like revisiting the derivations, revisiting the development to arrive at why it's so, and like so. Feynman says, the uncertainty principle, or Feynman or Leitner Sands, one of these three gentlemen, the uncertainty principle describes an inherent fuzziness that must exist in any attempt to describe nature. See, he's attached to kind of like a higher level concept. Kind of like the fourth dimension was like, what do you want it to be? You know? Because it's essentially, before it was like, the law is that the rule is determined by our place in space. And so the fourth dimension being let out was like, it's a fourth dimension. It could come and go. It's above. It is something you can just project into space, anything you want. So also this idea of the Heisenberg uncertainty is a great thing. Is like, it's not deterministic. You're not bound to your fate, whether or not free will is or is not falsifiable. According to this theory, it's not, which is nice. But in our mathematics, we need to find a way to make do with it later when it's like, well, I'm going to need that back. You already have one. Don't worry about it. The necessary uncertainty, the probability density. They close the chapter. In its efforts to learn as much as possible about nature, modern physics has found that certain things can never be known with certainty. Much of our knowledge must always remain uncertain. The most we can know is in terms of probabilities. Or ideals. Because you can know that 1 + 1 = 2. It's not going anywhere. So what you can, pretty much all you can know in a sense is like some of these ideals that are so perfect. Now, largely these are geometry, proportional form, and quantities and qualities of numbers. And then, of course, all the other things that ever been ascribed to be ideals before, like relationship with the deism, or fraternal, paternal, maternal, filial love, romantic love, all these kinds of things, hate, strong emotions, things that people see as true or that are real to them. That's going to vary quite a bit in terms of what these things are. But then in terms of the statistical nature of things and the probabilistic nature of things with regards to the scientific nature of things, then yeah, as Feynman says, it's like, well, yeah, we got statistics and probability to go with the validation and invalidation of the null hypothesis for statistics and probability. And then we got the scientific method with observables, reproducibles, and falsifiables. So that's all we can say, that our theory has been shown by what hasn't been disproven, and that it covers all the bases of all these, every other experiment. It's got to cover every experiment ever devised. That's why it helps sometimes when it's pretty simple. It's like, well, it adds up just what it was and what it will be, and the only machine is a lever, and there's both white and black holes everywhere, and the forces are combined, yet they're different, and then they're like, well, light is special, and this kind of stuff, and the fleeting of flux, and the superclassical, another great balance. Gravity isn't always working. It's the law. It's just on. These kinds of things that hopefully will help to, I found, then get into the mathematical theory, where it's possible to say, well, I got 3 laws of large numbers, at least 3 infinities, at least 3 continuities, at least 3 spaces of all the zeros and ones, or probabilistic events, at least 3 kinds of probability and 3 kinds of statistics to consider. And kind of the same 3 kinds, across those, which is even a bit more profound. That then get back to then for monist dualism, Heraclitus and Parmenides and Zeno of the Eleatics, and from the great antiquity of our modern canon and dogma, and as well combining and reflecting upon East and West and the prehistorical, and all what's come down as the mystical and the tradition and all this kind of stuff, the canon, and then the modern, and then saying, well, and yeah, we're going to keep scientism and logical positivism also, these kinds of things. That's the way that I found that it's most satisfying then for the overgeneralization to arrive at a comprehensive grandiosis of these things. That this is the sort of approach that is anybody's. I mean, of course, if anybody else came and said this, basically the exact same things, I'd have to say, you're right. All right. Well, I wish you a good day, and I shall so hope that you and yours are doing well and in good spirits and health and with good outlooks and prospects. And that what I came across with today was mostly just promotion of my own theory, a theory at all. And then as with regards to moment and motion, there's still then that's affecting the backdrop of the entire theory then to get into for fitting the parts together, that the stop derivative after the identity dimension, where what I've been studying is I've kind of been reviewing the identity dimension talks and the differential analysis. That's pretty real, and it's quite central in the mathematics and the objects of mathematics, and in the middle. So I'll be following up on that a little bit more. So for Zeno's swath, it's yet more about the same. That basically it's a straight line, and how it gets there, and of the distance traveled from point to point, at rest in the beginning and at rest at the end. Hey, have a great day. I shall, I'll try to come up with some more of this later. Luckily, though, we only covered like 5 pages in these books, and there's about 1,200 more, so there'll probably be something interesting in the stacks. So long, gentle readers.